Last time we finished off section 6.8. Let's start section 6.9, which is just theory of estimation with Microsoft Excel. Okay, so if you have a normal random variable, then, well, maybe I should write it as x. If you have a normal random variable, then to find the probability, yes, question, yes, it will be very similar to quiz one. Again, the problems will be identical to what is on the sample. It's just that instead you'll be getting 5 questions instead of the however many are on that sample. But yes, same questions, same way that we did it for quiz number one. Okay, so if I want to find the probability that, let's say, x is less than or equal to r, then the command you would use in Excel would be normal distribution, and it'll be r with mean, mu, sigma, and this will be true because you have a less than or equal to. If you wanted to find the probability that if you want to determine r, so that the probability of x being less than or equal to r is p, some given value p, then you would say that your r would equal the following command. So you would say norm inverse of p, and then you have mu and sigma as your mean and standard deviation. Next, if you had some t random variable with degrees of freedom nu, then if you wanted to figure out the probability that t is less than or equal to r, you would use the command t distribution r degrees of freedom, and again true because it's a cumulative. Okay. If you wanted to figure out the probability that absolute value of t is greater than or equal to r, then you'd use the command t distribution, and it's going to be two-tailed. So you have r and your degrees of freedom. If you wanted to do it the other way. And so let's say you want to do find the probability that t were greater than or equal to r. Then you would do the t distribution, but in this case it's going to be a right tail. Again, r and your degrees of freedom. If you wanted to find r given some given value p, then you would use the inverse. Okay, there you go. Then you do t inverse of p and your degrees of freedom. Hopefully I did go up far enough. Tell me when you're done. Okay, done. Okay. Next, if you want to do it the other direction, probability that t is greater than or equal to r is some given value p, and you want to determine r, then you use the command t right-tailed inverse, again with the given value of your probability p and your degrees of freedom. And if you want to figure out r, such that the absolute value of t is greater than or equal to r is some given value p, then you would do t two-tailed. Oh, t inverse two-tailed p degrees of freedom. And lastly, for chi-square, if you have some chi-square random variable with degrees of freedom nu, then if you wanted to figure out the probability that chi-squared is less than or equal to some value r, you could calculate that using the following command. Chi-square distribution r, your degrees of freedom, and true. Next, if you wanted to calculate probability that chi-squared is greater than or equal to r, then it would equal chi-square distribution, and that will be a right tail. And lastly, if you want to determine R, given some value P, then you would have the command chi-square inverse of P and your degrees of freedom. Okay, and you could calculate that. So those are the latest commands to give you these values that we've done before. Actually, I have an old version here of Office, and it has similar commands. So maybe I'll, for 1 second, show you this. Well, let me wait a second, and then I'll show it to you. Okay, so suppose you wanted to find oops. How about that? Let's say you wanted to find the probability that Z is that X, I should actually say X here, that X is less than 3.265, you would just say norm. Here they don't, for the older ones, they don't have the period dist, but it's norm dist. And you go 3.265 and say that the mean is 3 and the standard deviation is 1.4. And, well, since it's less than or equal to, you'd say true. If you wanted to do the same thing, except let's say that you have you want to find the probability, it's too hard to write in here. You want to find the probability that T is less than 3.265 with degrees of freedom 49, then you would just say T dot dist. Again, this one's an older one. They don't have the period. 3.265, comma, your degrees of freedom, 49, comma, and you say true, because it's a less than. Oh, here it's slightly different again. So let's say that we want to find the t-value, the t-value for having a probability of 0.01 with degrees of freedom 49. So that's just going to be our the same sort of quantity that we would have for the whatchamacallits, norm inverse. So you just say T inverse. So again, they don't have the dot. And the probability is 0.01, and my degrees of freedom is 49. And the same thing for chi-square, except here they just call it chi distribution. So the chi-square distribution. So you go chi SQ, then dot dist. And say you want to figure out the probability that chi-squared is less than 7.769 with degrees of freedom 5. You would just put 7.769, comma 5, comma true. These are slightly older commands, but okay. So really that finishes off section 6.9 Let me go on to section 6.10. Oh, and of course, well, there are TI-80 three commands you could also have done. I should have said that for. Okay, so forget that then. Oh, it is working. So say you wanted to find the probability, say you have a normal distribution. Oh, this is just going to take too long. Yeah, forget this. This is not, it's not responding to anything I click on. Okay, so forget that. Okay. You could also do it in the TID3 if that was responding. Okay, so let's go on to section 610. Eventually I'll come back on that. Okay, so section 610, extended topics and proofs in the theory of estimation. Okay. So let's do some things that we more or less went over. So first thing to show, theorem 6.1, if I have, say, x, some simple random sample consisting of x1, x2 to xn, and these are normally distributed. So suppose that each of these random variables are normally distributed with mean mu and standard deviation sigma. So we're drawing this from a normal population. Then the mean, the sampling distribution of all possible sample means, is normally distributed with mean mu and standard deviation sigma over radical n. Okay, so let's show that. Well, since each of these random variables are independent, and normally distributed, with mean mu and standard and variance, let's say, being sigma squared, then the expected value of the sum of these random variables. Well, we've seen that that's the same as the sum of the expected value of these random variables. And each of these expected values are just mu. Since you're adding up a whole bunch of constants, this is just in mu. And the variance of the sum y equaling 1 to n of xi. Since, again, these are independent, this will just be the sum of the variances and, well, each of these have a variance of sigma squared. So you're adding up a whole bunch of constants. So that's n sigma squared. So now let yi equal x minus mu over sigma. And also let z equal the sum minus n mu over radical n sigma squared. So let those equal. So then well, the expected value of yi is expected value of xi minus mu over sigma, which by the properties of the expected value is just the expected value of xi minus mu over the expected value of sigma. Well, sigma is a constant, so that'll just be sigma. And again, mu is a constant, so that's just the expected value of xi minus mu over sigma, but the expected value of xi is just mu. And so the expected value of yi is 0. The variance of yi is just the variance of xi minus mu over sigma, which is equal to, well, by the properties of variance, the variance, of course you're assuming that sigma is not 0, the variance of xi minus mu over sigma squared. And again, mu is constant, so it's a variance of xi over sigma squared. But the variance of xi is just sigma squared for each I. And so the variance is equal to 1. So the expected value of yi is 0. The variance of yi is 1. Next, Zn is equal to the sum I equal 1 to n of xi minus n sigma n mu radical n sigma squared. By definition, that's the definition of z. And so, by properties of summation, this is the same as the sum I equal 1 to n of xi. Oh, well, maybe I'll write this way. So this is the sum x equaling 1 to n. And since mu is constant, these are equal. And so by the properties of summation, this is the same as the sum I equaling 1 to n of xi minus mu over rad n sigma squared, which is equal to the sum I equaling 1 to n of xi minus mu over radical n sigma squared, which is just equal to yi. So this is equal to sum I equaling 1 to n of 1 over rad n, just taking out, writing the denominator as a square root of n times the square root of sigma squared. So xi minus mu over sigma. Question? There you are. Okay, sure. Hopefully that's far enough up, right? And so this is equal to the sum I equal 1 to n of, well, yi, because this in parentheses is yi, over radical n. So let me just wait here a second. Then I'll scroll up. Okay. Okay, good. And I should say that these are independent, identically distributed. These are independent and identically distributed. That's what I meant when I wrote that. So this is equal to if I look at e to the I t zn, this is the same as e to the I t, these guys. So that's the sum, let's call it k equaling 1 to n of y k over radical n. Just changing the name of my dummy index so it doesn't confuse with the other I that's there. Well, by the, so this is equal to e to the sum k equaling 1 to n of I t y k over rad n. By the properties of exponents, this is just the product of e to the I t y over rad n. But each of these are identically distributed. So this is equal to, well, k equaling 1 to n of e to the I t, let's just say the first one of rad n. Okay. And so this is just e I t, let's say y1 over rad n to the n, because all these are identical now. But this is normally the yi is normally distributed, and so this just looks like e to the minus 1/2 t squared. So this says, so therefore, the distribution of Zn, so this step here shows the distribution of Zn equals the standard normal distribution. And so the distribution of the sum of x I, by definition here, since this was normal, then this is going to be normal. And so this will be normal with mean and n mu and standard deviation radical and sigma squared. So the distribution of this equals, well, the normal distribution, where the mean was n mu and the standard deviation was radical n sigma squared. And so, just dividing by n, this says that the distribution of the means equals, well, it'll be the same thing, you just divide by n. So it's n mu over n radical n sigma squared over n. Well, the n's cancel. So that's just mu. And divide by n, so that's radical sigma squared over n, which we usually write as, sigma over radical n. And that's what you wanted to show. Okay? Good. So that was that comment that was made before the central limit theorem. Actually, this is very similar to, sort of the statement we had about the central limit theorem also. It's more or less, we could do it with this. Theorem 6.2. Which says that the sample variance is an unbiased estimator of the population variance. Okay. So let's show that. So first, the variance of xi is just the expected value of x minus mu squared and so this is just the expected value of x minus mu squared, which is sigma squared. Next, the variance of the sample means is just the variance of the sum of xi over n, which is just the variance of the sum of xi over n squared by the properties of variance. And again, this is the same as assuming independence as above. This is the sum I equal 1 to n of the variance of xi over n squared but from above we have that the variance was sigma squared, so it's a sum of sigma squared I equal 1 to n over n squared. Which is equal to, well, there are n of these, so it's n, and these are constant. So n sigma squared over n squared. And so I have sigma squared over n. Also, let's do a calculation that's slightly different. The variance is just the expected value of x squared minus expected value of x squared. Okay. And so, this is equal to the expected value of x squared minus, well, the expected value of the mean is just mu. And so, since we already shown that that's equal to sigma squared over n, we get that sigma squared over n is the expected value of x bar squared minus mu squared. And so we have the expected value of x bar squared is sigma squared over n plus mu squared. Okay, so let's keep that. Next, I have the expected value of the variance, sample variance, is the expected value of the sum of x minus mu squared over degrees of freedom n minus 1. And so this is equal to the expected value of the sum I equaling 1 to n of x minus mu squared all over n minus 1. And so this is equal to the expected value of, and so let's multiply this out. So this is by the special product formula, the sum I equal 1 to n of x squared minus x bar xi plus x bar squared. And so this is equal to again, by the properties of the summation, is the same as the expected value of the sum xi squared I equaling 1 to n minus the mean, the sum, oops, where's my 2? Special product formula, 2, times the sum I equaling 1 to n of xi plus the sum of these. Well, there's a constant, so I can just bring them outside the constant. Maybe I'll just say that these are constants. I'm adding up n of them, so it's n. Okay. So this is equal to by the property the fact that this is the sum I equaling 1 to n of x I squared minus 2 the sum of x is just n times x bar, so you multiply by another x bar, that's x bar squared plus n x bar. But now you can combine those, so this is just the expected value of the sum of xi squared plus nx minus because they're subtracting two of them, minus nx bar squared all over n minus 1. Okay. And so this is the same as the sum of the expected value of xi squared. Oops, that's wrong. Of xi squared all over n minus 1 minus the expected value. Well, you bring that out. That's just going to be n times the expected value of x bar squared. Okay. And so this is just the expected value of xi squared minus. Now we already figured that out from above. Oh, I wrote it wrong here because that's there. I wrote something slightly wrong right here. So I'm looking up to find it. So I already found that that's equal to n sigma squared over n plus mu squared all over n minus 1. Okay. And so we have that this is equal to the sum I equaling 1 to n expected value of x squared minus sigma squared minus multiplying the minus n inside the parentheses mu n squared all over n minus 1. But the variance is just the expected value of x squared minus expected value of x quantity squared. So this is just going to equal the sum expected value of x squared. So it's the variance of xi plus the expected value of xi squared. Minus these last two things, sigma squared minus n mu squared. Equals, let me move these over so I have enough room to write. Okay. Minus n mu squared all over n minus 1. Okay, good. And so this is equal to the variance of xi there it is. The variance of xi is sigma squared so this is sum I equal 1 to n of sigma squared plus, well, the expected value of xi, well, we already found that also. That's just the, well, we found it above in the previous proof. That's just mu. So minus sigma squared minus n mu squared. And those are just constants. And so this is going to equal n sigma squared plus n mu squared minus sigma squared minus n mu squared all over n minus 1. Obviously the n mu squares cancel, and so you get n sigma squared minus sigma squared over n minus 1. Factor out the sigma squared. You get the n minus 1's cancel. So that's sigma squared, and that's what you wanted to show. So you wanted to show that the expected value of the sample variance is indeed the population variance. Okay. Let me do the next. Lemma. Which is PQ is maximized when P equals 1/2. So when we did calculations involving when we didn't know the population proportion, I said, well, just let it equal 1/2 because this will always give you the maximum sort of error. And so it turns out that P times Q, again, Q is 1 minus P, will be maximized when P is indeed equal to 1/2. So let's look at this. Well, PQ equals P times 1 minus P, which is equal to P minus P squared. So let me write this in descending order, this polynomial. So I can see that this is quadratic in P. So therefore, its graph looks like a parabola. And so PQ is a parabola. The constant in front of the square is less than 0. So this parabola points down. And so since the parabola points down, it has a maximum at its vertex. Okay. And so, well, recall the formula x equaling negative b over 2a. So that's where the x-coordinate of the vertex would be located. Well, we don't call it x in this case. We call it p. And the constant in front of the p is plus 1. Constant in front of the a is minus 1. And so the maximum occurs when p is 1/2. And that's what I wanted to show. Okay. So let's actually show the theorem that what I said, that the variance, or in this case the standard deviation, is maximized. The standard error is maximized when p equals 1/2. So the statement was that I said that the error, the standard error is maximized when p is 1/2. So here's the standard error. So let's show that this is maximized. Well, I have that the standard error is just radical pq over n. Okay. And well, n here is a constant. So the only thing that varies is p and q. Well, of course, q is related to p. And well, we will maximize this when p and q are, when p times q is maximized. And this is maximized when p equals 1/2 from the above lemma, since pq is maximized. And p equals 1/2 by the above lemma. And that's what you wanted to show. Okay. Lastly, let me just say something about the normal quartile plot. So this is a way to visually look to see if a particular distribution is actually normally distributed. Okay, so suppose we have some data. So the first thing is sort the data in from lowest to highest, so in ascending order. And let's call that x1 to xn. Okay. For each call it xj. Determine the z value so that the area to the left of it so to the left of this particular z value is two j minus 1 over 2n. So plot the points And maybe I'll call it the z-value, and I'll call this z-value name the z-value, this z-value, yi. Yj, we're doing it for xj, yj. So for each xj, you have some z value. We'll call that z value yj, and this z value is such that the area to its left is 2j minus 1 over 2n. Okay, so plot the points xi, yi. Okay, and that's called the normal quartile plot. Okay, and so if they look to be on some particular line, then it will be a normal distribution. So long as they're close to the line and they don't have some systematic pattern. And so as long as they're just sort of randomly placed near a line by looking at this plot, then it will be normal. Okay, so if these points lie randomly near a line, then the data came from a normal distribution. Okay, and of course, there will be programs that will actually do this for you. That really finishes off chapter 6. So let me go on to chapter 7. Leave that for a second. Okay, so let's start this. Chapter 7. Hypothesis testing. And this will involve one for one population. Chapter 8 will be for two populations. So, section 7.1 is just an introduction, a quick introduction. Hypothesis. So this is a statement, a claim about a particular property parameter obviously for a population. The hypothesis is that the population mean is equal to 12. The hypothesis is that a claim that the population variance is greater than 3. Things of that sort. A hypothesis test. This is a statistical procedure for testing a hypothesis, a claim for testing. I'll just say a hypothesis, which is a claim about a population parameter. So somehow I want to test the claim that the population mean is greater than 12. Okay, so examples of this. Um, some institute claims that its method allows couples to increase the probability of having a baby girl. So that would be an example of something that we could test. Another, a newspaper cites a survey and claims that the majority of people have heard about Kindle. And so that's another statement that we can test. Um, it is claimed that the body temperature is 98.6 degrees, and we go out and we have a sample of, say, 106 body temperatures, and their mean is 98.2. We can use this data to test the claim that the mean body temperature is 98.6 degrees. Okay, so that's really about all for the intro. Let me go on to section 7.2, which is actually much longer. Uh, okay. Oh, this is working. That's working now. Okay, good. Okay. Section 7.2, the fundamentals of hypothesis testing. Okay, so a hypothesis test will consist of the null hypothesis, yeah, that was it. That was it. It was just a very quick intro to what we're going to be doing. This section will be now putting in all the sort of pieces that we missed from section 7.1. Okay, so the hypothesis test will consist of the null hypothesis, the alternative hypothesis, and a level of significance. Okay. So we denote the null hypothesis. So a hypothesis test just consists of these three objects: the null hypothesis, the alternative hypothesis, and the level of significance. The null hypothesis is some claim, some statement about what the population parameter is equal to. The alternative hypothesis is a statement about what the population parameter is not equal to. A level of significance is some value that is given in order for us to use to do this statistical test to test the claim of the hypothesis. This value, the level of significance, will be a number between 0 and 1. I guess it could equal 0 or 1. It never would, but I guess technically it could be a value between 0 and 1. It could equal 0 or 1, but you would never. Matter of fact, there are only a few values you would actually let it equal. Um, you don't want it to be too small nor too big. It's really only between 1 and 10%. Um, Now, the alternative hypothesis is some statement about the population parameter, which is how the population parameter differs, how it's the opposite of the null hypothesis. The null hypothesis is some claim about what the population parameter is equal to, and we'll use that value that is equal to in the hypothesis, in the statistical procedure to test the hypothesis. Once we have formed my hypothesis test, we will collect data and actually perform the test. So we will perform the hypothesis test. When we perform this hypothesis test, we will collect data and compute a test statistic. And then we will check to see if this test statistic lies in some region, the rejection region, or if it does not lie in the rejection region. This rejection region depends upon your value of alpha, the level of significance, and it also depends on the sampling distribution. Okay. This test statistics will depend on the data that you've collected and upon the sampling distribution. So this data will be some, from some sample, and it'll have some sort of distribution. Okay. Please notice that the null, alternative hypothesis, level of significance, these are already formed before we collect the data or anything. So these don't depend on our data, on our sampling distribution. These are all fixed before we perform the hypothesis test. We can then draw some conclusion. We could also, instead of rejection region, maybe I'll just put in parentheses or a p-value, which depends on my sampling distribution. And so the p-value actually depends on the test statistic. And the sampling distribution. Okay. You can either look at the rejection region or a p-value. We'll most do the rejection region. Once you have performed this, you will then make some sort of conclusion. Then draw a conclusion. Okay. Okay, so let me sort of say this again. So a hypothesis test will be some claim about the population parameter. So it could be that I claim that, let me call theta my population parameter. It could be the population mean, population proportion, the population variance, whatever it is. I just called it theta. That, let's say it's equal to some value. Call it theta naught. The alternative would be that, well, the opposite of that is that's not equal. And we'll have some level of significance. Or my hypothesis test could be as follows. Maybe I'm saying that this value is greater than some value. The opposite of that is that the population parameter is less than or equal to some specified value. Or maybe we'll have another case. It could be the alternative hypothesis says that it's less than some value. The null hypothesis says the opposite, that it's greater than or equal to some value. And of course, we have some level of significance. This is called a two-tailed test. This is called a right-tailed test. And this form is called a left-tailed test. Let me just draw a distribution. And let's say that my statistic is t. Okay. And suppose it's nice and symmetric or something. So suppose it looks something like this. Again, it's whatever. It doesn't have to be symmetric or anything. I just do it that way. For the two-tailed test, if I look here at this alpha, then the total of these two areas here of the two tails will equal alpha. If I look here at my right tail test, the total of the right tail will be alpha. If I look at left tail test, the total area of the left tail will be alpha. These values here are called critical values, which make the area equal to alpha. So this is my critical value. This is my critical value. Please note that if you look at the alternative hypothesis, say greater than, notice that this arrow points to the right, and it's right-tailed. This arrow here points to the left, so it's left-tailed. And well, not equal, therefore it points in both directions. This region here, it's called the rejection region. Where I have filled in my value, which has alpha. So this is my rejection region. And here's my rejection region. In this case, there's both of these sides are rejection regions. Okay? So, please note the following, that you should always look at the alternative hypothesis to tell where the tail is, because some people always write equal for the null hypothesis. So there will be some people that will write equal always for the null hypothesis, and it's a valid point to put it equal there, because when we do the hypothesis test, we're actually assuming that the null hypothesis that it actually is equal. But I myself don't do that. I like to write the null hypothesis as the opposite of the alternative. But you can never be safe because other people will do it another way. So always look at the alternative hypothesis to see where the tail is in order to, well, actually do the hypothesis test. Always look at the alternative hypothesis. Okay. Some people call the alternative hypothesis the research hypothesis. So you'll also hear that terminology. Okay, so example. Assume that 100 babies are born to 100 couples treated with the X-sort method of gender selection. um, that is claimed to make girls more likely. We observe 58 girls in 100 babies. Write the hypothesis. To test the claim. That the XOR method that with the XOR method the proportion of girls is greater than 50%. Okay. Let's do this. So first, recall that a hypothesis test only looks at a population parameter. So let me write down null hypothesis, alternative hypothesis, and alpha. Okay. So if I look here at this statement above, it's talking about the claim is the proportion is greater than 50%. So we're talking about a population proportion. And so let me write down the, well, first off, before I do anything, alpha is always the easiest thing to determine. So let's look at alpha. If I look here, they don't tell me what the level of significance is. If they don't tell me the level of significance, we always assume the level of significance is 0.05. So since the level of significance was not specified, then it's always equal to 0.05. So I should probably say that up here, that in general, so I assume it's equal to 0.05, and in general, it's always between 1% and 10%. So even though I said it could be between 0 and 1, it really is only in general between 1% and 10%. And if we don't specify the level of significance, it'll actually be, I'll assume it's equal to 5%. Okay, now let's finish the rest of this. So that was easy. Level of significance 5%. Now, notice that we're talking about a proportion. So we're talking about a population proportion. So we're talking about something involving P. It says it's greater than 50%. If you notice in all the above, the null hypothesis involved an equal sign. The alternative hypothesis never had an equal sign in it. So whatever doesn't have an equal sign will be the alternative hypothesis. It says greater than, so I'll put greater than 50%, so 0.5. Now, I always do the opposite. The opposite of greater than is less than or equal to. And that is my hypothesis test. Okay. Let's do another example. Determine if the following hypothesis test is one-tailed, two-tailed, right-tailed, or left-tailed. So I have the null hypothesis, p equals 0.4. Alternative hypothesis, p is not equal to 0.4. Alpha equals 0.05. So I want to determine if it's one-tailed or two-tailed. Well, I look here at the alternative hypothesis. The alternative hypothesis says not equal. Therefore, it will be a two-tailed test. So I just look at the alternative hypothesis. Alternative hypothesis said not equal, two-tailed test. And I'm done. Next, do another example. Did I? So since the alternative hypothesis has a not equal, then it's a two-tailed test. Okay, next, determine the following hypothesis test is one-tailed, two-tailed, right-tailed, or left-tailed. The null hypothesis. Now again, I'm doing proportion. It's greater than 0.8, less than 0.8, and alpha is equal to 0.05. Okay. Well, again, I look at the alternative hypothesis. Since the alternative hypothesis has less than, well, notice that that's pointing to the left, therefore it's left-tailed. It's a one-tailed test, it's left-tailed test. Oh, I guess I should say that these are also called one-tailed test because you have one tail either right or left as opposed to the two-tailed test. Look how many tails you have. So it has one-tailed and it's to the left, so it's a left-tailed test. Okay. Let me just say this in the p-value method. Let me just write this down. So the p-value method, if your p-value is less than or equal to alpha, your level of significance, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. If the test statistic is within the rejection region, we reject the null hypothesis. If the test statistic is not in the rejection region, then we do not reject the null hypothesis. Okay. You should never say you accept. Notice that we're always either accepting or we're not accepting well, let me not say except. Either we're rejecting or we're not rejecting the null hypothesis. Never say we don't say anything about the alternative. We are always testing the null hypothesis. So in hypothesis testing, you're always testing the null hypothesis. So that's why I have here that I reject or I do not reject the null hypothesis. Also, um, it is better if you never say that you accept any claim because there could be further statistical evidence that you can present where maybe what you thought was true is not really true. And so all we can say is either there's enough evidence to reject a claim, or there's not sufficient evidence to reject a claim. So either you reject or you do not reject the null hypothesis. You should not say that you accept it. Um, okay. Next, type 1 and type 2 errors. Okay, so we have this procedure, and well, this procedure can do things. So let's say that we have, this will be, reality. So say that the null hypothesis is true, or the null hypothesis could be false. So this is reality. So this is what really happens. Now we perform our hypothesis test. And so when we perform it, we'll make some sort of decision. And either we will reject the null hypothesis, so this will be some hypothesis test, or we do not reject the null hypothesis. So this will be some sort of decision based upon the wow. Sorry, based on the hypothesis test. Okay. So this is the true nature of the hypothesis test of the null hypothesis. So it could be that the null hypothesis really is true, or it really is false. Of course, in reality, we never know that. But either the null hypothesis is either true or false, and we perform some hypothesis test. So we can suppose that the null hypothesis is false and we reject the null hypothesis. Well, then that's good. I've made a correct decision. So this is good. Suppose the null hypothesis is true and we did not reject the null hypothesis. Okay, good. So that means that we thought the null hypothesis was true. So this, again, was a correct decision. If I have a true null hypothesis, and so the null hypothesis is actually true, But we go through our hypothesis test and we reject the null hypothesis, thinking that it's not true. This is called a type 1 error. If the null hypothesis is false and we think it's true, we don't reject it. By doing this hypothesis test, we go, oh, it looks fine to me. This is called a type 2 error. So we can think of a hypothesis test as a courtroom where you have a lawyer and you have some null hypothesis that's on trial. And so let's sort of restate this in the sort of idea of looking at it as a trial. So we have this null hypothesis and it's going to trial. It's either actually innocent of the crime or it's guilty of the crime. And, it's either actually done the crime or it didn't do the crime. And well, it goes to trial. And well, before you go to trial, you should know the amount of evidence you need to convict this. Meaning, how much evidence do I need so that, I convict this guy? Do I need 100% of evidence? Do I have to be 100% sure he's guilty? Or maybe, well, I just have to be 95% sure he's guilty. And, 5% of the time, if I accidentally, convict someone who's innocent, that's okay. So, before I go to trial, I need to decide upon alpha, the level of significance. That's the amount of evidence I need to convict, meaning how much am I willing to convict innocent null hypotheses. And so the null hypothesis goes on trial. If he is innocent, the null hypothesis is innocent and he's found not guilty. So if the null hypothesis here is innocent and he's found not guilty, we do not reject the null hypothesis, then we have made a correct decision. Justice has been served. If the null hypothesis is guilty, he did commit the crime, he goes to trial, and the jury convicts him. So we have rejected the null hypothesis. Again, justice has been served. A correct decision has been reached. If the null hypothesis is innocent, yet he goes to trial and he's found guilty, we reject the null hypothesis. We do not think the null hypothesis is innocent. We reject it. Then that is called a type 1 error. The probability of having a type 1 error is denoted by alpha. And so alpha, the level of significance, is the probability of having a type 1 error. And so it's the probability that you reject the null hypothesis, even though in reality the null hypothesis is true. So what is the probability that you will reject the null hypothesis given that you assume that the null hypothesis is true? Beta. Now, suppose, let me tell you what that is. Suppose that your null hypothesis is guilty. And so the null hypothesis is really false. So you have a guilty, you have a null hypothesis that has actually committed the crime. So the null hypothesis has committed the crime. However, he goes to trial and they do not reject the null hypothesis. They do not find that he's guilty. And so they let the null hypothesis go free. So that is called a type 2 error, where you have let a guilty null hypothesis go free. You have you did not reject a null hypothesis that was indeed false. The probability of having a type 2 error is called beta. And so, in general, we fix the level of significance alpha because we know what is our tolerance for, executing innocent null hypothesis. So what's what level of significance, what is our tolerance for convicting innocent people? We call that alpha. In general, most people pick 5%. And so somewhere between 1 and 5%, 1 and 10%, as I said before. Now, um, you in a hypothesis test, what we do is we fix alpha, and then we try to minimize beta given alpha. So we know this is our tolerance for convicting innocent null hypotheses. I want to minimize the number of guilty null hypotheses that we let go free. And that is what we call a hypothesis test. Okay. And so notice the following. Um, so controlling type 1 and type 2 errors. Because you would probably say, well, why don't we just, have 0%? I don't want to ever let, ever have an innocent null hypothesis. I never want to convict an innocent null hypothesis. Okay, you can, why don't we do that? Well, notice the following. So if I fix alpha, then an increase in your sample size will cause a decrease in beta. So that's good. Next, if you fix your sample size, then a decrease in alpha will cause an increase in beta. So unfortunately, that's horrible. If you try to make, if you try to get fewer and fewer type 1 errors, you get more and more type 2 errors. So if you say, well, I want to decrease the amount of convictions of innocent people, that means you increase the non-conviction of guilty null hypotheses. And so you're letting more and more guilty null hypotheses go free. Similarly, if you increase alpha, you'll decrease beta. Okay. If you fix beta, then increasing n will decrease alpha. Okay. And so What this means is that basically, uh, if you want to improve things, increase your sample size. Okay. But in general, what happens is uh, there's this play between type 1 and type 2 errors. The less type 1 errors you have, the more type 2 errors you have. The less type 2 errors you have, the more type 1 errors you have. So no matter what you do, if you decrease one, the other will increase. And so you can't make alpha too small or you'll increase beta. You can't, and of course you don't want alpha too big because you don't want to convict too many innocent null hypotheses. So you have to find this sort of balance between the type 1 and type 2 errors. So in general, we will let alpha equal 0.05 unless otherwise specified. And we really never have alpha less than 1% and never bigger than 10%. Okay? Okay, so let me do an example. Assume that we are conducting a hypothesis test. Of the claim that a gender, that a method of gender selection increases the likelihood of a baby girl um, so that the probability of a baby girl is greater than 0.5. So A, identify a type 1 error. Identify a type 2 error. Okay, so let's do that. So a type 1 error is the error of rejecting a true null hypothesis. And so in a type 1 error, we would conclude that the probability is greater than 50% when in reality it is not. So you conduct some sample, and you in this sample, there are a lot of baby girls. Therefore, you conclude that the probability is, of having a baby girl is greater than 50%. But in reality, you just happen to, you pick a sample with a whole bunch of baby girls, and that really didn't, but in general, this method doesn't really have more baby girls. So your data falsely led you to this conclusion where you thought that there were more baby girls, but in reality, there's not. So a type 2 error. So a type 2 error is an error where we fail to reject the null hypothesis when in reality the null hypothesis is false. And so um, a type 2 error is where in reality um, the number of baby girls is greater than 50%. Yet um, we conclude that the evidence does not show this. So we conducted a sample, and there were very few girls in this sample. So we conclude that, well, no, it's not greater than 50%. But in reality, it is bigger than 50%. And so that's a type 2 error. Power of the test. So a power of a test. So the power of a test is just 1 minus beta. So if I look at beta, the probability of having type 2 error, if I look at its complement, so what's the complement of having a type 2? What's the probability of not having a type 2 error? That's called the power of a test. So 1 minus beta is the power of a test. Okay. Note the following. The way that I'm setting up a hypothesis test is not necessarily the same way that you'll see your hypothesis test being set up. It really depends upon what major you're in, how the hypothesis test will be set up. So, in the physical sciences, The alternative hypothesis is what you are researching. It's your research hypothesis. So whatever your research hypothesis is, that will be the alternative hypothesis. Yes. Mm-hmm. And so any sort of physical science, so cosmology, whatever, that will be your research hypothesis, is your alternative hypothesis. In the social sciences, the null hypothesis is what you're researching. So your null hypothesis is whatever your research hypothesis is. In sociology, your null hypothesis is whatever the data tells you is true. So whatever makes the null hypothesis a true statement is your null hypothesis. So they look at their data, they go out, and sociologists are always true because they have stated their hypothesis so that whatever it is, they're always correct. So null hypothesis is always true. And they always let the level of significance be 5%. Okay. And lastly, for mathematicians, because we don't research anything, nothing physical at least. All of our research is abstract. So for mathematicians, the null hypothesis is the one that has an equal sign. So whichever one has an equal sign will be the null hypothesis. For economists, it's the one that gives you the most benefit is the null hypothesis. And so there are many other ones that do differently. So just note that the way that the hypothesis test is set up will be different depending upon your major. So we will always do it where I just look at the equal sign. Okay, whatever one has an equal sign in it, if it says equal, less than or equal to, greater than or equal to, that's the one I'm going to use for the null hypothesis. If it says less than, greater than, not equal, then that's the alternative hypothesis. So the one that doesn't have an equal sign is the alternative hypothesis. Okay, so maybe I just sort of say that. The steps in hypothesis testing. One, you want to identify the claim to be tested, and you put it into symbolic form so it looks like a hypothesis test. You select your level of significance, and this is based upon, your tolerance for type 1 error. What is the seriousness of having a type 1 error? And if your level of significance is not specified, then we assume the level of significance is 0.05. You go out and collect some data. You will then determine, well, from your parameter, you'll determine what type of sampling distribution you have and calculate your test statistic. You'll then calculate the rejection region and determine if your test statistic lies within the rejection region or not. If the test statistic lies in the rejection region, then you reject the null hypothesis. If the test statistic does not lie in the rejection region, then you do not reject the null hypothesis. And then if the hypothesis was, if the problem was stated in words, then you must rewrite your conclusion so that it is a statement that is easily readable in non-technical and simple terms. Okay, so that really finishes off section 7.2. Let's go on to section 7.3, where I'll actually perform some of these hypothesis tests. Okay, so section 7.3, testing a claim. About a mean and let's suppose that the population variance is known. Okay. So let's do an example. So I'm given the following hypothesis test. The null hypothesis is that the population mean is 4.8. The alternative hypothesis. By the way, sometimes they use the letter A to denote alternative hypothesis. I just use one. That the mean is not equal to 4.8 and the level of significance is 0.05. So notice that this is my hypothesis test. Notice that this is a claim about a population parameter, the population mean. We then go out and collect some data. And here's some data that they collected. The sample mean was 4.8. The population standard deviation was 4.7. And the sample size is 81. Okay, so let's solve this. So the first thing I notice is that this is a two-tailed test because I look here at the alternative hypothesis and I see, well, it's not equal, therefore I have two tails. Okay, next I'm looking at a sampling distribution, a sample means. Since our parameter is a population mean, then our data will be a whole bunch of sample means. So we go out and collect a whole bunch of sample means. And so the sampling distribution is sample means. Since I know the population variance, then this will be a Z, a normal distribution. And so this will be Z. It's two-tailed, so I want this area here, these two tails. It's going to be symmetric. Each of these will have half the area. So this area here would be 0.025. This area on this side would be 0.025. I then need to find the critical value. I can look in my table, or let's see if this works. 0.025. Let's see if, oh, it's actually working. So I'll do inverse norm. good, of 0.025. That'll give me, well, actually, that will give me one end, the negative, negative 1.6. So negative 1.959963986. And the positive part, obviously, if I do, actually, let's just do this. 1 minus, was it 0.05 divided by 2? That'll give me the other end, which is just the positive part, which is the positive 1.959963986. So this is my rejection region here, what I've drawn. Okay, let's try that again. Rejection region. Okay, good. So now let's find the parameters of my sampling distribution. And so the mean for the sampling distribution of all possible sample means is just equal to the population mean. Well, please note, to find this parameter, you always look at the null hypothesis. So let's just look here at the null hypothesis. And that's why people will write the null hypothesis with always an equal sign, because you're assuming, no matter if this said less than or equal to, greater than or equal to, whatever, you're actually always assuming that it's equal to this value. And so I'm assuming the mean is 4.8. Done. Now let's figure out the standard deviation for the sampling distribution of all possible sample means, which is the population standard deviation divided by the square root of sample size. And so we have that the standard deviation of the population is 4.7. The sample size is 81. And so, really, actually, I wrote this wrong. I wrote it wrong. It's 0.8. That was a typo. And so the population standard deviation is 0.8. And so if I do that, I get 0.08. A bunch of 8s there. And so now let's determine the test statistic. Well, you've already seen the test statistic. It's just, in this case, well, let's see. I have a z, so it's z. And what is z equal to? Well, z is x minus mu over sigma. And so for all the rest of these hypothesis tests, from now to the end, almost for now to the end of the semester, that's the formula we use, z equal x minus mu over sigma. And so x is 4.7. Yeah, so 4.7 minus 4.8 over 0.088. Oh, that's a nice number, isn't it? So this is equal to a negative 1.125. So now that I have found this test statistic, now what I do is I plug this back into the graph here to see if it's in the rejection region or not. Well, let's see. And maybe I'll leave it with more, well, I'll maybe put it with red. So it's a negative 1.125. But notice that this is not in the rejection region. Since this was not in the rejection region, we do not reject the null hypothesis. Please note, you always have to write that you're rejecting the null hypothesis or that you are not rejecting the null hypothesis. So do not reject the null hypothesis. That's it. Okay, let's do another example. So I have here radiation emissions. So listed below are the measured radiation emissions. This is in watts per kilogram, corresponding to a sample. So 3.8, 0.55, whoop, not 3.8, 0.38, sorry, start all over again. 0.38, 0.55, 1.54, 1.55, 0.50, 0.60, 0.92, 0.96, 1.00, 0.86, 1.46, 2, 4, 6, 8, 10, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 4, 6, 8, 10, 11. Good, there are 11 numbers there. Okay, so use a 0.05 level of significance to test the claim that cell phones have a mean radiation of level that is less than 1 watt per kilogram, with the assumption that the mean is 0.48 watts per kilogram. Okay, good. Of course, I'm also assuming that we are sampling from a almost normal distribution. From, let's say, an approximately normal distribution. Okay, so let's do that. Okay. So I have a null hypothesis, alternative hypothesis, and level of significance. Well, the level of significance is 0.05 because they tell you it's 0.05. The claim is that the mean is less than 1. So the claim is that the mean is less than 1. Now, we put this in the alternative hypothesis because less than does not have an equal sign in it. The alternative hypothesis is that it's greater than or equal to 1. Okay? And so let's test this. Note that we know the population variance. Therefore, so that says that our sampling distribution will be normally distributed. Okay, so let's draw this. So my sampling distribution will be Z. Notice that this is less than, and so since this is less than, then this will be a left tail test. And so we're looking at this area, which is 0.05. Okay. So we can look in our table to see what that is, or I can do this on the TI-83, which is actually 0.05. So let's do that again. There it is. And so it's 0.05, and I get negative 1.644853626. And that's my rejection region. So here's my rejection region. Okay, good. So now let's determine the parameters. For my sampling distribution. The sampling distribution of all possible sample means. Well, the mean for the sampling distribution of all possible sample means is just the mean of the population, which in this case is assumed to equal 1. So notice that even though it says greater than or equal to, I know in my head I really say equal. I just wrote it less than or equal to because it's or greater than or equal to because that makes it the opposite of this, and it's more sensible saying that. But I know that we're testing where it's equal. The standard deviation for the sampling distribution of all possible sample means is sigma over radical n, which is equal to sigma is 0.48. N is, let's see, how many things did we have? Oh, n is equal to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 of those. Plug that into your calculator. And so you should get 0.1447254. Let's actually go out and determine my statistics. So the mean is equal to sum over n. Well, I've got a TI-83, so let's plug that in. And so I have here the data was 0.38, 0.55, 1.54, 1.55, 0.5, 0.6, 0.92, 0.96, 1, 0.86, and 1.46. Let's store that in L1. And now let's do one var stats L1. You don't even need to write L1 here, but I will. And so you get the following. The sum is 10.32. N is 11. And the mean came out to 0.93818. A bunch of 1/8. Okay. We don't need the sample mean, the sample standard deviation or the sample variance, even though it actually told us here what the sample mean is, 0.42286668,391. But we really don't need that. Okay, so now let's compute the test statistic. So to compute the test statistic, I have that z equals x minus mu over sigma 0.9381818181 minus mu 1 over sigma 0.144724454. Plug that into your calculator. Negative 0.427141074. So let's plug that into here. So that's negative 0.4. And so I'm here at a negative 0.427 141. 714. This is not, so here's the rejection region over here. It's not in the rejection region. So I do not reject the null hypothesis. Now, we had this hypothesis test where it was a whole bunch of words. So now we have to actually write the conclusion in words. So just saying, do not reject H sub 0, that tells us nothing unless you actually know what the hypothesis test is. So they're asking us to test the claim that cell phones have a mean radiation level that's less than 1. Notice that we did not reject the null hypothesis, which meant we didn't reject this, which meant we rejected this guy. Oh, but this guy says less than, which is our claim. So we actually rejected the claim. So, no. So, no, there is insufficient statistical evidence okay, 1 second. Statistical evidence have to go down a little bit to figure. And so, no, there's insufficient evidence to support the claim that the mean radiation level is less than 1 watt per kilogram. And that is your answer. Okay, I'll scroll up for a second, and I'll scroll back down. Maybe I'll go up here, wait for a second, and then scroll down. Let me scroll down unless people squawk at me and say, oh. Let me wait here for a little while and then continue. Okay, I can probably continue down. Okay. Okay, so that concludes section 7.3. Let me go on to section 7.4. Actually, section 7.4 is really not going to be any different than section 7.3. Actually, all of the further sections are really all going to be the same. Once you have this section down, that you see what I'm doing, all the other subsequent sections are going to go pretty fast because they're all very similar to this. Okay, so let me continue with section 7.4. Okay, so section 7.4 Testing a claim. About a mean. In this case, the population variance is unknown. So in this case, we're just going to be doing the same thing, but we're going to be using a t-test rather than a z-test. But everything else will really work the same. So let me do some examples. Suppose the null hypothesis. Population mean is greater than or equal to 15. Alternative hypothesis. Population mean is less than 15. And alpha is 0.01. So that's my hypothesis test. We go out and we collect a whole bunch of data. And I have that the sample mean is 14.7. Sample standard deviation 0.5. And the sample size is 61. Okay. So let's solve this. So first off, I notice that the sampling distribution of all possible sample means is going to be, well, a t-distribution. Maybe I'll just put the t here. Be a t-distribution because I do not know the population variance. And since we have the alternative hypothesis being less than, then I will have a left tail test. Alpha is 0.01. My degrees of freedom are 60. I can look at my table, but I'm going to be lazy. So I could look at the table, but let me do inverse t. And this is, was it 0.01? And degrees of freedom was 60. Okay, so if I do that, again, I could actually, if I did it correctly, we get the right answer. Okay, so you could also look this up. There it is. You could also look this up in your table in the back of the book, and you'll get the same answer. But we've done those before, so I'll just do it on the calculator. And so I get a negative 2.390, which is what you get in the table, 119457. So that is my critical value. There it is finally. Okay, so let's try to calculate the test statistic. To do that, let's calculate the parameters. And so the mean, the sampling distribution of all possible means, is the population mean, which is assumed to be 15. The standard deviation of the sampling distribution of all possible sample means, because we assume that the population is infinite, is the population standard deviation over the square root of the sample size n. We don't know the population standard deviation, but we can approximate it by the best point estimate, the sample standard deviation, Well, the best point estimate for the variance is the the sample variance, and we can estimate the population standard deviation by, well, the sample standard deviation. It's not the best point estimate, but it is a point estimate. It's biased, but the best you can do with the square root of sample size, 61. So plug that into your calculator. You get 0.0641844. Okay, so now let's calculate my test statistic. So my test statistic is equal to z equal x minus mu over sigma. Well, of course, we're not really using x, but t, because it's a t distribution. So the mean was 14.7. The mean for the sampling distribution of all possible sample means was 15. The standard deviation 0.06401844. So plugging that into your calculator, you get negative 4.68614. 9806. So that means, wow, you're way out here. It means you're way, well, actually even further than that. You're like out here. So you're way out over here at negative 4.686 9806. So you're certainly in the rejection region. So you reject the null hypothesis. Okay, now, since there were no words associated with this, we don't restate it in words. We only restate the conclusion in non-technical, simple words if there is some story that came along with this test. So if there's some words that came along with this test, some story that I could write about to give this conclusion in this little story, these nice non-technical, simple words that convey this idea of what I want to say about the conclusion of the hypothesis test. But in this case, we have no words. So you just say reject or do not reject the null hypothesis. Let me do another example. John a college student, in a statistics course. Is interested in IQs of students. John believes that the students at his college. Oh, is that why it said that? At his college are gifted. A gifted student as an IQ over 120 with the help of the instructor John surveys. Okay, 1 second, and I have to see if we're going to, you'll still be able to see me. John, oh good, didn't seem to do anything yet. John surveys. "52 students." And let me just look for 1 second. I didn't lose you guys, did I? You can still see everything and hear me, correct? Still good, still good, good, good. Okay, sometimes when I put in the charger, it kills you guys. Okay, so, but it didn't. Okay, so let's see. Surveys 52 students and finds that those students IQ are normally distributed with a mean IQ score of 113 and a standard deviation of 10 with a 3% level of significance test the claim. Okay, so let's do that. Okay, so first note that the population that we're studying here are all the students at Johns College, and what we are measuring is the IQ scores of these students. And notice that this came from that the IQ scores are normally distributed. And so this is a normal random variable, our random variable being that we are measuring IQ scores for students at Johns College. So the population parameter that we're going to be considering will be the population mean. And we go out and we collect a sample of 52 students. So our sample size is 52. And we have a mean for the sample of 113. So my sample mean is 113. And we have that the standard deviation of the sample is 10. Since we do not know the population variance, that means that the sampling distribution here will be a t-distribution. Okay. And that my degrees of freedom will be 50, since my sample size is 50. No, Sample size 52, not 51. I remembered it wrong. My sample size is 52, not 51. So my degrees of freedom are 51. Okay. The hypothesis test. So the claim is that students at St. John's College are gifted. So the claim is that the IQ scores, that the mean IQ scores, are more than 120. Since this does not have an equal sign, my alternative hypothesis is that the population mean is greater than 120. The opposite of that is less than or equal to 120, which is our null hypothesis. And they tell us that we want our level of significance to be 0.03. And so this will be a t-distribution. My sampling distribution of all possible sample means is a t-distribution. And we want it greater than. That's the alternative. And so my rejection region lies out here to the right. The degrees of freedom, as I said, was 51, and alpha is 0.03. I can determine my critical value either by looking in my table, seeing if they have 51, which actually I don't think they do, or by using linear interpolation and the z approximation to t to calculate it. Or, I'm lazy, you could use this. And so you could just say, well, I want, let's see, so it's 1 minus, this is a 3%, so 0.03. Degrees of freedom was 51. And your answer is, oops, try that again. So your answer is 1.92356205. You could also, just using linear interpolation and that approximation formula, I actually did it by hand. And remember that your table, I'm using tables, so my table is only accurate to 3 decimal places. I get the critical value is 1.9242, so almost there. Yeah, 4250446. So it's accurate to like 3 decimal places, so that's not bad. Considering the table is not anywhere, actually, table is even less accurate than that. It's only 2 decimal places, so getting that it's almost 3 decimal places still is pretty good. Okay, so let's figure out some of the parameters for my sampling distribution. So my parameters, the mean for the sampling distribution of all possible sample means is the mean of the population, which I said was 120. The standard deviation for the sampling distribution of all possible sample means is the population standard deviation over the square root of the sample size, again because the population is assumed to be infinite. The sample mean, the sample standard deviation. The population standard deviation is not given, but the sample standard deviation is given as 10. So I'll use that as an estimate for the population standard deviation. And the sample size is 52. Plug that into your calculator. 1.38 0491. And so I have that t, the test statistic, z equal x minus mu over sigma. And so the sample mean was found to be 113. The mean for the sampling distribution of all possible sample means is 120. The standard deviation for the sampling distribution of all possible sample means is this long number. Plug into your calculator, so you get a -5, no way, 0.4771786. So you're way out here at a -5.04771786. Okay, good. And so you do not reject the null hypothesis. Now, since this was stated in words, I'm testing the claim that students are gifted, meaning they have a larger score. So I'm testing this claim that they're gifted, and we did not reject, so we thought that this was true, so we rejected this. So no, they're not gifted. And so the conclusion is no, there's insufficient statistical evidence to support the claim that the students at Johns College are gifted. So that is your answer. So again, if you have some sort of story, then your answer must be given as a story. Let me do another example. Big Burger claims that its senior citizen employees work an average of 16 hours per week. In a random sample of 10 senior citizen employees working in the area Big Burger outlets. The average number of hours worked per week came out to be 21 hours per, 21 hours. And with the standard deviation of 5 hours. Test a claim. At the 1% level of significance. Assuming the number of hours worked per week is normally distributed. Okay, so let's do this. So the null hypothesis. So the claim is that they work an average 16 hours per week. So the null hypothesis is that the mean is 16 hours per week. The alternative hypothesis is that it is not 16 hours per week, and we want to do this at the 1% level of significance. Okay, good. This is a two-tailed test. We do not know the population standard deviation. We know population variance. We know a sample standard deviation of 5. So that says that the distribution here will be a t-distribution. The degrees of freedom is, well, they asked 10 people, so n is 10. So the degrees of freedom is 9. And so let's draw this. I would say about 10 more minutes. So not much longer than that. I'd say 10 minutes will be done. Okay, so this will be a T. It is two-tailed. The total area is 0.01 for the combined total. Okay. Again, you can look this up in your table, or you can do inverse T. Okay, so let's do that. So 0.05 plus, this is minus. This is 1%, so 0.01 divided by 2, with degrees of freedom 9. With a typo here. There. Okay. Okay. 0.5 What the? Sorry. There's a little bit of a lag, so it's something it's hard to hit things. Okay, that should be it. Okay. Oh, and it still has the minus in there. Maybe it would have been faster just to look up in my table. Okay, finally. Okay. So inverse t 0.05, 0.5. I just love having errors. Okay. Sorry. Okay. It's 1 minus it. Finally. Okay, so that's the answer. Yes. I know. Okay, so it is, there's your answer. It is, and there's two of them. So this is 3.249835541 and negative 3.249835541. Okay, so those are the critical values. Okay, good. So just it's a little slow because of that. Okay, so let's find the parameters. And so the mean for the sampling distribution of all possible sample means is the mean of the population, which we assume to equal 16. The standard deviation for sampling distribution of all possible sample means is the standard population standard deviation over the square root of the sample size. Since the population is assumed to be infinite, um, I don't have the population standard deviation, but I have a sample standard deviation of 5 with a sample size of 10. Plug that into your calculator. You get 1.58113883. Let's calculate my test statistic. Z equals X minus mu over sigma. And so the mean was found to equal, came out to be 21 hours. So the mean was 21, and my mean for the sampling distribution of all possible sample means is 16. Standard deviation of all possible sample mean is 1.58113883. Plug that into your calculator. You get 3.16227766. 3.1. Ooh, just missed it. Oh, just missed it. So here it is right here. So 3.16, sorry. 3.16227766. Okay? And so you do not reject the null hypothesis. So I didn't reject the fact that they were equal. And the claim is that they were equal. So, yes, there is insufficient statistical evidence to reject the claim. That the average senior citizen employee at Big Burger works 16 hours per week. And that is your answer. Okay. Now, okay, so really that's about it. Okay, so that finishes off section 7.4, and then I guess that's it for today. Oh, exactly 10 minutes. Okay, so that's it for today.